So yes, so as I mentioned, we are talk about the simulation, and then so the many type of the simulation. Okay, so the multi-paradigm simulation, I will define what it is, and then how do we use this simulation for online, as well as the hierarchical manner for the such a complex systems of the systems. And then let's talk about the ideas that how simulation, I can see that simulation already widely used in process mining, but again, let's see the some opportunities actually together. So what is a simulation? Okay, so simulation, well, given a real system, like this order fulfillment center in Amazon or Walmart or anything like that. And then the models, okay, that I learned that there is an expert in, okay, I put the PitchNet there. It can be PitchNet, formal model, event graph, any type of this logical model, or it can be like a lot of the differential equations or different equations that are used to represent the behavior of those systems. And then all that are combined to execute the simulation. Okay, so that's actually the simulation. So let me show you a few different type of the simulation that people are working. So first type of the simulation, well, this is the simulation of the order fulfillment center that we just look at it. And this type of the simulation is called the discrete event simulation. That is probably most relevant with this process mining and process model. And there are many other commercial software, but I happen to use just this Flexim, but it can be Arena, Simio, okay, AnyLogic, or many. Okay, it's exactly the same thing. Okay, so second type of the simulation. So this is a simulation of the university campus during COVID. Before I joined the Purdue 2022, I was at University of Arizona for 22 years, and during pandemic, I worked with the university leadership and public health to simulate. These are actually large classroom, over 575 the students, and at that time, the major challenge of the university president at most of the university is when we can open up the class. And then such a large classroom that how many percent of the class, okay, be the safe to open. And so these type of the simulation is called the agent-based simulation. And then one of the simulator used is AnyLogic, but there are many other type of the simulators as well. Okay. So those are second type. You see a lot of the social distancing that actually many of you may not want to see, but again, that's the kind of the simulation that allow us to see how many percent of the classroom, and also this kind of classroom has like 6-7 doors, and what kind of is a random policy would be better, or you want to dedicate some rooms to only entrance, others for only exit. Also, will we be able to handle 10 minutes will be sufficient for the class to come in and the existing class to go out. And then it's not only about the time and congestion, so we work with the public health people to see that if one of us is potentially exposed, what is the average time that we are close to within 6 feet and 3 feet, 6 feet, and then what are the time and those type of the health-related simulations are being done as well in this agent-based simulation. So the third type of the simulation, okay, so this is an emergency in a city, okay, and this is a physics-based simulation, and I don't know you're familiar with the Unity game engine, Unreal. If you use the NVIDIA Omniverse, they continue to develop lots of the libraries and tools, right? So this is actually model already outdated several years ago, but the model actually for this type of the physics-based simulation is pretty detailed and the cute, right? So let me just fast forward. These are like a city view, and upper here, that actually this is the city from the top view, and then so this is emergency that okay, that the project that I was doing with the Department of Homeland Security, if there is an emergency, then how do the people actually behave during the emergency, the situation, okay? So this type of the simulation is physics-based, the simulation. Okay, so then I just showed the three different kind of the simulation. And why do we use the simulation? So, well, that simulation, once we develop a credible simulation that allows us to do what-if the analysis, first of all. The second, it actually generates a scenario that doesn't exist. So some of the work that we are doing a lot is, of course, everybody does this, the transformers and generative AI stuff, and then that actually the tools allow us to create a lot of the environment, the scenario that doesn't exist. So a lot of the agent-based simulation, we use this generative AI capability to generate the simulation scenario that doesn't exist. Okay? So third, simulation mostly runs faster than real time. Of course, 99% of the simulation runs faster, but if the simulation is really, really, really complex, then that can be very, very slow, right? So that's why that's another benefit of the using simulation. Okay, so that was some very quick overview of the simulation, and let's look at a little bit more formal, introduction of the discussion of the simulation. So I call it multi-paradigm. So simulation, the word. Okay, computer simulation. Okay, many of them are computer simulation and discrete event simulation. Well, simulation, the goal is the same. The goal is we want to develop a model that represents the real system in a most accurate and valid manner, right? So it's all mostly the similar, but there is a little bit of the difference. So discrete event simulation, just like the example that we saw from the order fulfillment center, the entity is relatively passive, and each entity is driven by these processes, all the expert of the process, okay? So entity, patient, okay, enters the hospital, then we are driven by the process to go through the system. So each entity, person is relatively passive, okay? That's actually the discrete event simulation. How about agent-based simulation, like a student in the classroom? So we are not passive. We are observing. We are, the perception, reasoning, and then we make our own decision and planning. Okay, so it's a relatively entity is more active. Still, we are doing exactly the same thing, but we are more active than passive, discrete event simulation. Okay, that's actually agent-based simulation. The third one is a continuous simulation, just like a physics-based simulation that I just showed you for the emergency evacuation, but another type of the more aggregate than discrete event simulation, something called a system dynamic simulation that is based on the differential difference equations. Okay, so those are three major types of the computer simulation. Then what is the non-computer simulation? Well, physical, simulation, like nowadays, simulation involving hardware in the loop, like a digital twin that I will show you some example. How about human in the loop? Simulation that integrate the human in the loop. So those type of the simulation cannot run faster than real time. Because people or hardware needed to be in the loop. So the clock there is going to be the real time. Okay, I'm going to show you a few examples of this physical the simulations as well. So these are multi-paradigm simulation. Then let's just discuss a little bit of the similarities and some of the key differences between those different type of the simulation. Let me use the simplest possible example. Okay, so the queuing, for those people working on queuing theory, MM1 system, okay, that one machine, get a one part arrival, and then those, following the Markovian process, okay, the inter-arrival time follow the exponential distribution, and then Q has an infinite capacity. So this is the simplest possible the example. For this, actually, the other case, so if for those working on discrete event simulation, how long does it take to develop such a MM1 system? If you use any commercial software, it takes 15 seconds. You just drag three, okay, this whatever building blocks, This happened to be called the arena, okay? But again, any type of the simulator, it doesn't take longer than 15 minutes. Okay, that's actually how long it takes. However, if you want to use a discrete event simulation software to represent more active entity like an agent, okay? So I still use the same discrete event simulation, but in this case, the customers going to the restaurant, if the line is too long, some people, we may not be that patient, so after 1 minute, 2 minutes, some of them may leave, right? So how do we, or again, our human behavior or this more active behavior, we can provide more detail. But if we want to represent this type of the more active the entity agent, then exactly the same model can be a lot more complex. Okay, so this agent, the discrete event simulation, this is more like a conceptual paradigm, but you can still use discrete event simulation to represent more active the agent. Of course, there is a software, there is a commercial simulator that allow us to describe more active behavior that I can show you some example in a minute, okay? So those are discrete event simulation and agent-based simulation I just quickly compare. How about system dynamic models and agent-based simulation, and what are the building blocks of those two other major simulations, okay? Let me use this product innovation, the graph. I don't know what the next iPhone, the version is, but again, whenever new mobile phone comes in, this is the there is innovators that always buy, purchase the product to early adopters and so on, okay? So in terms of the buying behavior over time, it curve looks like that bell curve. And then if you look at the cumulative distribution, it's something similar to the S curve, okay? That's a very simple, product, adoption type of the graph. So how can I represent this product adoption graph using system dynamic model and agent-based simulation? Again, we are doing exactly the same thing. Simple, very, very simple example. I'm going to even simplify more, further, that instead of this S curve, I'm going to just use the linear. Cumulative is linear. In order to do that, then the buying behavior is a uniform distribution throughout the time. Okay? So let me use that as example. So next one. So if you look at it, the buying behavior on the left-hand side, that's what's called the system dynamic model. It's a people, whether it is, let's say, the 10,000 people purchasing, this iPhone in certain area, 10,000 people is considered as like a liquid, okay? And then because it is a constant over time, it reduces in a linear manner. That's actually system dynamic model. Agent-based simulation, instead of using liquid, we treat each individual as a discrete agent. Depending on the computational power you have, it can be individual. One agent can be one person, or one agent can be 10% or 100%, depending on the resolution of the model that you want to represent, okay? So, but if you look at right-hand and left-hand side, the time, over time, is going to be exactly the same. At the end of the time, both of them, the potential adopters, they adopted this new technology, okay? So that's a conceptual difference between system dynamic model, agent-based simulation. So let's look at next one. Then, what are the building blocks? So for the discrete event simulation, building blocks can be like a PageNet or event graph or some type of the formal model, right? The graphical representation. For the agent system dynamic model, it's just something called, the bottom part, it's something called the, stock flow diagram. Stock looks like the containers, and then stock has outgoing rate and incoming rate. Okay, so that's actually the flow. And then in this case, again, the R, the rate is the constant, but it can be more complex. On the right-hand side, the building blocks of the agent-based simulation is that this is a state chart, okay, state space model, okay, that each individual agent, we are in certain state, and then after a certain delay, okay, that they just leave that state. So probably before purchasing state, after a certain time, I become the purchased state. So that's actually agent-based simulation. And then this delay is uniformly distributed. Okay, so that's a building block between system dynamic model and then agent-based simulation. Well, are we really modeling exactly the same thing? Yes. I'm not going to derive these equations today. That's why I spent time to develop this kind of the movies diagram. Okay, but if you look at the again left-hand side, you can actually, this is a simple possible system. So you can solve this differential equation so that system is A equal to A0, whatever the initial value, minus RT. R is the constant, right? So over time, it's linearly decreasing. Okay, that's easy. How about the right-hand side? Right-hand side, each individual agent, their delay time is uniformly distributed. The total time is A0 over R. Okay, that's actually the final time that everybody purchased the behavior. So what we can do here is, if you take the PDF probability density function, in this case is uniformly distributed. If you take a CDF, cumulative, so CDF means all the delay time was right now or less than me, right? Less than right now. So that delay time is less than now means the people who have purchased the new product already. That's a CDF. So CDF multiplied by number of the agents using that expected value, that will result in exactly the same, this system equation. So we can, for the simple problems, we can actually mathematically, we can prove that system dynamic model and agent-based simulation that result in exactly the same system equation. Of course, as the system gets more and more the complex, then the level of the detail that we can model, system dynamic model cannot catch up with the agent-based simulation, right? Otherwise, system dynamic is a lot more, right? The aggregate, computationally less demanding, so you can use system dynamic model, but the level of the expressiveness is not as good as the, of course, agent-based simulation. Okay. So there was I think all I said here is a discrete event simulation, system dynamic model, agent-based simulation. That's exactly try to do the same thing. There are certain differences, but that's actually the difference. So there was another short discussion about the multi-paradigm simulation, and let me talk about online and hierarchical use of these simulation. Let me begin with the online. Okay, so this happened to be my dissertation topic, real-time simulation-based planning and control. That actually 2000, right? So 24 years ago. At that time, we didn't call it digital twin, but that's actually what it actually does. And I'm going to show you two examples for the manufacturing. Earlier, it mentioned the digital transformation and manufacturing, but for the first case, manufacturing. The second case, the UAVs and ground vehicle for the some of the Arizona border control that I'm going to show you some example there. So I don't know, any of you been Purdue University campus before? No? I hope you visit Purdue sometime, okay? So this is the new building, that we just opened the last January, and this is our school. We are in charge of this lab, and we call it Gateway Complex Lab, and a little bit over 10,000 square foot with a high bay. So it has a lot of the machines, and you see the AMRs, autonomous mobile robots, the same robots that are used in the Amazon warehouse and PepsiCo, the order fulfillment centers and so on. And then on the lower left-hand side, that's actually the scanners, the scanners that scan the finished product so that we can do the quality control. okay, and then this, of course, the ASRS, and also we don't have the flying robots yet, but we are ordering a lot of the flying robots so that we will do the logistics, the area that use a lot of the, the flying robots for the inventory control as well as the delivery of the product. And we have a faculty doing 3D printing directly from the mobile, actually flying robots as well. Okay, so these are the system that we play in our the schools. Okay, so they're all connected using digital, right? So, okay, I actually simplified for the discussion. Okay, so how can you do the digital twin? So this is a very busy slide, but let me look at the left-hand side. We call it simulation-based planning. This one is nothing new. This is a textbook information, traditional use of the simulation, right? Just like the first discrete event simulation, you want to develop a simulation, and for each of decision point, you want to employ the different type of the policy, and then multiple policy, multiple rules, and then you do the statistical analysis to identify the best policy. So that's a simulation-based planning. Okay, so nothing actually new here. And right-hand side is where digital twin comes in. Okay, but before we do that, let me talk about some of the decision problems that needs to be addressed during the planning the situation. Okay, so traditionally, I don't know if there is any expert in this shop floor actually control, but traditionally for each part, their part routing is linear. Okay. Regardless of the condition of the factory, the part routing is linear, so not many decisions to be made. Okay. However, nowadays, a smart factory that instead of fixing a lot of the routing, we leave a lot of the alternative, and then the decision we let it to be made by the smart the controllers and computer. Okay, during the because machine can be broken down, and then that, right? So that's actually the key difference between traditional and then smart the factory. And in terms of the objective function, of course, the manufacturing factory, then we want to either minimize cost or maximize the productivity without, right, maintaining the product quality. But so the project actually we are doing with one of the local company in Arizona, we were doing with a company in Arizona was energy. Okay, that I don't know I'm not sure about the situation in the U.S. here, but in the especially those area employing a lot of the renewable energy, like a solar energy in state of Arizona, right? This energy is actually big deal. Okay, the reason is, so this is one of the graph. So we put the power meter to the big machine, and then the bottom figure here is the energy consumption of the one machine for 15 hours, and I just magnify that to the top part here for 3 hours. And if you look at y-axis is a kilowatt, the energy consumption of the one machine when machine is on. If you look at when machine is on, even if it's on, it can be as much as above 12, or it can be 4, 5. So the same machine for 3 hours, it can be 3 times and 4 times of the energy consumption. That can be the difference. And then this medium-sized company has more than 50 such machines. And Arizona, during the summer, that they turn on many, many air conditioners so that this energy peak, that's a huge energy saving if you curtail, right? Reduce this peak, actually, the energy. So this is very simple kind of the problem. And then so in this kind of the situation, when, as I mentioned, we leave a lot of the alternative, okay? So that we let the smart controller select the part routing depending on the current electricity or current machine condition and so on, so that when this part is, when this part is done, which, because the part routing has a lot of the alternative, when I go to the next machine, should I pick the available machine? Should I pick the machine with the less remaining time? Or should I pick the machine with the less energy? Okay, that by just employing this simple kind of the policy, we were able to save a lot of the electricity bill of that particular the company, okay? So that's actually right-hand side. But again, decision, it can be any type of the production decision, maintenance decision, any type of the decision, okay? That's not the focus of the talk here. Let's look at the right-hand side. Once you found a good policy from the predictive analysis of your simulation, whatever the best found policy can be used on the right-hand side. In this case, is a simulation-based real-time control. In that sense, this is not simulator. It is actually real-time controller. But as you may know, right, that whether it's nowadays a lot of the commercial discrete event simulator, it can run predictive analysis, but you can just change your clock in real time, so the simulation runs in real time. And also, instead of the simulating your event or future task, in this case, you generate a command and send that command to the robots and machines and conveyor belts, okay, instead of the simulating, using exactly the same simulator that was used on the left-hand side for the predictive analysis, okay? So that's actually the simulation-based real-time control. So how does that work? Well, before I do that, since there is a lot of expert of this PitchNet and I guess finite state, machine state automata and so on, if you are familiar with the discrete event simulation, usually when we develop simulation, we don't, okay, so the level of the detail is a little bit above than control. Okay, so these are actually the number of the building blocks needed to represent a very simple one robot and one machine. Robot just put the part to the machine, and then how many a process, the graph is needed? Not many here. However, when robot put the parts to the machine, robot puts it, machine needed to grasp it, and then a robot is allowed to open and then leave. That many synchronization is a lot more detailed than traditional use of the discrete event simulation. That's why we use the the state machine, finite state automata, embedded into this simulator this is a supervisory level that controlling one robot and one machine, and then this is the finite state graph that controls the individual machine, and this is again state machine for this machine. And so once this type of the formal graph using this model-driven architecture, a lot of the software is again, I see a lot of the expert computer science information systems, so code can be automatically generated, right? So all the system, my dissertation 24 years ago was, you just configure your machine's robot and any factory facility. If you click a button, then digital twin simulation for the predictive as well as the control purposes that are automatically generated. That was the work, right? So I just developed a simple cartoon to see how actually this one works, right? So this is a right-hand side of the real-time simulation. So the top one is, again, it's a simulation, but it's not simulating. It is a controlling, generate. So what it does is, we have a robot, we have a machine, and this is a simplified graph that governs robot, machine, and the middle one is the supervisory controller, okay? So robot does not know who the robot puts the part with, right? It just does what the supervisor asks him to do. And the machine, the same thing, okay? Whether person is doing or robot is putting, just to open the door, close door. So when I run the simulation generate the task, and then send it to the robot, and the robot physically picks the part. This is event coordination, so whether it takes 5 seconds or 2 minutes, okay, simulation waits until robot finishes the picking the part. And then for the simplification, I didn't send the completion messages. For each task, completion needs to be sent back to the controllers. I didn't include it, okay? And after that simulation, what it does is it just asks the machine open the door, physically open the door, and the completion message goes back, and simulation asks, now robot put the part, and then so, okay. That was how the digital twin, concept was used for the predictive analysis as well as the control. So nowadays, digital twin everywhere, right? So if our lab, the big lab that I showed you using NVIDIA Omniverse, right? IJAX Sim, that's actually a particular tool that. So this type of the digital twin, like a robot, how many joints, like a 6 kind of the joint, and you just link every joint and with the physical and digital, so that this type of the digital twin that you physically change the robot, then digital, of course, in real time changes. Model, if you change your model, physically change. We just sync, right? So this kind of the polling from the software digital perspective, that's a relatively easy, but however, for the more like individual component. However, if you apply this one to the huge, this is one university lab, but even the bigger one, connecting every single sensors in the continuous manner, that's actually easy to connect, but I don't think that that's the right approach, right? So it needs to be hybrid. That how do we define, just like we did in the event-based, right? How the model and the real physical system needs to be, synced. I think that needs to be the key in terms of the developing digital twin for the large scale systems, okay? So let me put it that way. So now, next few minutes, I'm gonna talk about the automatic simulation model generation. I see actually the IEEE, the work group that I heard that there is a effort of the standard development, and then also I saw that like a process, the mining community, that there is a work that PitchNet model is automatically generated and so on. I saw your papers in your community, but let me talk about some of the model generation work that we have done for the simulation. So this is a very old paper, but so the efforts when I was working at NIST. NIST is a standard organization in the U.S. So I was a guest researcher there. And the goal was we try to develop a library of the simulation object. So developing simulation object for the general purpose, that's almost impossible. So we want to narrow down for the simulation object for the manufacturing shop floor. And for that, actually, we defined neutral description. So that's actually where the standard comes in. Later, this work form a basis to become a real standard that I will show you, but this is a prior work, So that once you develop neutral description, then we develop this model builder, and model builder generate this particular simulation, commercial simulation model automatically, and then that is given to this simulation engine, so the simulation can generate the data for statistical analysis, or it generate the visual animation, for the visualization, and then it goes back to the user. So this is again very old work, and at that time, this information model, I don't know any of you heard about it, used actually this something called the Express G, model was actually used to define object for the general manufacturing, the simulation, and then for that. This is a simple, the shop floor available in Penn State University at that time, and then we populate, this database, to just populate, describe your, manufacturing system, and then from that neutral file, that this is automatically generate simulation model for the arena. The first one is Arena file, one of the Rockwell, this is by the Rockwell automation software. And then the bottom one is another popular, simulation called the Pro model. So that was actually some of the early work. Later, that become the CISO's, again, it's still led by NIST. I was one of the member, okay, but the paper that I showed form a basis for the, this actually the work. And then, so there is this standard is called the CMSD, Core Manufacturing Simulation Data. And that's a standard of the CISO, Society of Simulation Interoperability Standard Organization. And then for this one, instead of using Express-G as information model, that they use this UML, okay, Unified Model Language, especially the class diagrams. Okay, of course, many big industry leaders were participating to help us to develop these standards. And then for this one, so the simulation, there is a layout information, there is a product part information, there is a production operations information, planning information, resource information, and then some admin support information, and then each area that actually further extends. Okay, so I'm not going to go to the detail. And then for the actual representation of this information is done by the XML. So that's actually the CMSD standard. And so this is a case study of this CMSD used for one of the big, actually, the companies. And so the pro model on the right-hand side, that's a discrete event simulation. And right-hand side, the process simulate, that's a Siemens simulation. That graphic it's getting more detailed than traditional discrete event simulation. And design profit is some software, it's more aggregate, does the cost estimation, okay, time estimation type of the software. And then bottom one, capacity tool is Excel-based, the home developed, their industry developed their tool. The big company, many different departments, they are using different software in their life cycle to do exactly the same thing, to estimate time and cost for a given product. Okay, so instead of there is a manual errors and there are information, so everybody does manually, but using this CMSD, a lot of the information that was used in upstream of the design profit or Excel tool can be used for the discrete event simulation. Much of the information can be used to provide the input for the process simulate using this core manufacturing CMSD, the standard. Okay, so that's actually the standard efforts. So I will make sure to leave some time for our discussion and the Q&A. Okay, so I have only a few more slides actually left, but so this is some other type of the application applying this digital twin planning and control instead of the manufacturing. This looks like Arizona, okay, the desert. And so this is again the project that the bottom part, there is there is the border area, there is a drug traffickers and there is people we want to, it can be animals or, again, drug traffickers that we want to just identify and follow, okay? So we use a lot of the sensors, and then second level, we use a lot of the drones, and then third one is actually the big balloon called this is, aero, we call it aerostat. And so the kind of the information that they use in the aerostat is this large area, right? The 30 miles, 40 miles of the area. And if you just magnify one of the area, this is what one of the UAVs actually see. But the ground, okay, if there is trees or so if there is a occlusion there that we cannot see from the ground, so the ground we can see from the more like a horizontal view. So we want to use different type of the sensors like UAVs and ground vehicle so that we can do the information fusion to best track the object or the animals of our interest. So that's actually our project. So I just skip all the slides and I just show the simulation, okay? Exactly the same thing, how the simulation is used to support the planning and control purposes. And so this one, again, this is very outdated. That's how the tools are getting better and better. Unless you pay attention, sometimes it's not easy to which one is real and which one is just simulated, right? So the top part is the real scene in Arizona that So one of the park, and this is the aerial vehicle. We put the cameras, and then this is what real aerial, the UAV is seeing it. And then this is what the ground vehicle, what they are actually seeing. And then bottom one is the game engine that I mentioned, the Unity. Okay, so that's so in this case, if the people they enter the shelter, then UAV cannot see the people going to the shelter, but the ground vehicle can follow, so that we can fuse this both information to the best the follow this the people. Okay, so in this case we happen to use physics actually the base the simulation for the digital twin. So next I'm going to use how about the hierarchical. Okay, I'm sure that this process management, I'm sure that this hierarchy is, especially if you look at the more complex, actually, the processes. Okay, so let me just, show the one project involving this hierarchical the simulation. So the manufacturing one, I just used the one facility, and Min-Suk mentioned that I do the supply chain. So how about we apply this one to the supply chain, top floor? A number of the multiple actually the facilities. So that's actually hierarchy, right? So in this case, the one way that we can accomplish, develop the this simulation is, one way is, I'm not going to, I don't have a video for this one, but this is each facility in supply chain has its own simulator. Instead of developing a simulation from scratch, how about we just link, okay, that the simulation that already exists in their partner company. That way, also the company, not only it's easier, but also they can hide any proprietary information that they do not want to share with their partners. Okay, so this is actually one way that we can accomplish this hierarchy is we just integrate already existing simulation. The second way that we have done using this multi-paradigm simulation is that, so the first simulation, supply chain, we just use this red part, only system dynamic model. You remember the fluid reservoir? Instead of the treating individual product, so this system dynamic is a lot more aggregate, so the computation is a lot faster. So that we use this simulation, system dynamic simulation, to identify good control policies in terms of the supply chain. Once good policies develop, then we use the integrated discrete event simulation in distributed computing environment to check the feasibility of the plan that was identified by system dynamic simulation. Okay, so that's actually one way that we address the hierarchy one. How about even for given the same facility, I'm sure that you haven't seen that. Probably it's not practical that we change the fidelity during the simulation run, right? But this is a National Science Foundation project that if your process, okay, so this graph, what it shows is given a product. This is one of the class project of our students, like assembly of the clock. Okay, so this is like we call it feature graph. So that whatever feature that needs to be produced to develop that components of the clock. Okay, so but if you think about the airplane or complex parts, right, this graph will be very, very, complex. But in your shop, depending on the level, if you're only looking at the machine level, if you look at the cell level, or you look at entire facility level, the area of your focus actually will be different. So there is a lot of the graph transformation depending on the level in your hierarchy. So our simulation, what we did here is on the left-hand side, the traditional simulation, like 99% of the people are doing now. When you run discrete event simulation, you never run the fidelity of your model for different departments. You just use the same levels of the process graph, right? But on the right-hand side, we just observe the performance of the particular area. If everything looks okay, you just continue, but something becomes suspicious, then you go down to the more further level so that you just turn on the additional sensors and you can observe actually more data. So we accomplish this adaptive simulation with different the model detail over time. So that's actually also how we address this hierarchy. So my last topic then. Okay, so the simulation for the supporting process mining. I'm still very new, right? The learning process mining. So I said I simulation how to support actually this process mining. So I have only one slide actually for this, right? So when I look at the the process mining, the area. So simulation, whatever type of the simulation, it generates the event and then logs, right? So the information. And then, so the goal of the process mining, seems that we want to discover, identify the processes from the simulation, the outputs, or outputs from the real, actually the systems. It's kind of the reverse engineer, right? Simulation generate the data, but from the data, we want to develop underlying models for the simulation, right? So the use of the simulation for the, supporting process mining, well, whatever the ways, the technology that you use to discover, identify the process, probably we can use a simulation to test or conform the generate the process. I think that's actually, I'm sure that this is already done already. Second, I see the standard efforts, that just like we try to generate a particular type of the pitch net, colored pitch net of any particular type, that, again, I know that there is some type of the reference model for the large, the process mining, for the large scale industry. But again, any type of the reference model, like a CMSD, that's one of them that I mentioned, So can we use actually this CMSD for the automatic simulation generation? So then there needs to be the methods and tool needs to be developed, right? From the log data, mine the process to generate the simulation. And the third one is, of course, once you identify this process, this simulation itself is not useful, right? We need to use a simulation to conduct a what-if analysis. Well, there is a simulation optimization. We want to do a lot of the meta heuristics to improve, enhance, identify the processes. That's actually another opportunity of the process mining, which I'm sure that a lot of the work is actually ongoing. So talking about simulation, so I learned the ICPM actually the conference, and being a board member of this simulation, there are a conference called the Winter Simulation Conference, and that's actually governed by a number of the society that includes a society like Informs, and society like IISE, as well as ACM. So there are multiple societies supporting this simulation conference called the Winter Simulation Conference. It's winter. Always conference is December. And then this year it will be Orlando. Next year will be Seattle. And then 26, every third year we try to go out of the US, and that happens to be Scotland in 2026, and so on. So hopefully, if the interest in exploring more about the simulation, hope that you have some of you in our simulation conference in the U.S. as well. So summary. I talk a lot about simulation, different kind of the simulation with the different case studies and applications. But so multi-paradigm simulation. I'm sure that you are most familiar with the discrete event simulation, but there was more aggregated system dynamic model, and then exactly the same thing, but more active, the entity perspective called the agent-based simulation that I mentioned. The second one, online. How do we use this simulation for the digital twin aspect, especially for the controlling the manufacturing, smart manufacturing, or the border patrol involving multiple hardwares. And then a hierarchical simulation that distributed computing environment, you can integrate the existing one, or you can use a multi-paradigm simulation for more aggregate for the higher level, and then discrete event simulation for more detailed level. And then we just discussed about how we can support, okay, your great work in this process mining work, okay? So I'm gonna stop here, and I can take any questions that you may have. Thank you for attending Keynote.